So as Dominique said, I'm currently at Google, but this work actually was done while I was at Defense Labs. Defense is a startup company that's working on basically using threshold cryptography for wallet as a service applications. So for those of you who are interested in cryptocurrency, right, one of the big challenges with cryptocurrency is managing the private key. And Defense is basically providing a platform for allowing users to manage their keys using threshold cryptography. I don't know exactly what the background of everyone in the room is, but threshold cryptography in general, and we'll talk more specifically about distributed key generation in a moment, but threshold cryptography in general, it basically allows you to take a private key and split it across multiple devices, multiple servers, such that even if an attacker is able to compromise some fraction of those servers, they don't learn anything about the private key. So this research was done in that context, in the context of actually trying to develop a product that they could deploy in their system. So I guess, as I was saying, the goal of threshold cryptography at a very high level is to share a secret key among a set of n parties, such that some threshold of them, in this case, I'll use t+1 for the threshold required in order to use the key. So any t+1 of those entities with their shares of the key should be able to perform some cryptographic operation, while at the same time giving the guarantee that an adversary who compromises up to t of those machines and learns t of the secret key values held by those machines doesn't learn anything about the key, and furthermore can't perform the cryptographic operation. So in our context, well, in this context of this talk, it doesn't really matter, but in the context of defense, the goal was to share a signing key so that t+1 of the machines would be able to sign transactions, whereas an attacker compromising up to t of the machines would not be able to. And there are, in general, two components of any threshold system. First of all, there's the initial sharing of the key itself. And ideally, you'd like this to be done by a key distribution protocol. This would be a protocol that the n parties themselves run in an interactive manner in order to generate both the sharing of the secret key as well as the corresponding public key. Sometimes there are systems in which this is done by a trusted dealer, but if you do it via a trusted dealer, then at the time that the key is created, that dealer becomes a central point of compromise. And if an attacker would be able to compromise the dealer during that initial phase, they would actually learn the entire key. So it's better, therefore, to do this initial the sharing of the key via a distributed protocol, so that even if parties are corrupted during the execution of that protocol, the attacker still doesn't learn anything about the key. After you've designed the distributed key generation or the DKG protocol, you then have to construct a protocol for performing the cryptographic operation itself, like in this case, generating a signature from those n parties. In this talk, we're going to focus only on the first of those. We're going to focus on the distributed key generation portion, and we're going to leave the second out of scope. As we'll see, the distributed key generation protocol that we develop can be plugged in and used with a variety of different threshold protocols for signing, decrypting, what have you. And we're going to focus on fully secure distributed key generation. I'll talk a lot about what exactly that means in this context. And we're specifically going to focus on distributed key generation in the discrete logarithm setting. We're going to define security by defining an appropriate ideal functionality, basically telling us what sort of a functionality we want to realize, and also what security properties we want the protocol to have. That's all going to be defined via an ideal functionality. And this gives us a very modular way to construct threshold systems in general, right? Because once we have a distributed key generation protocol that we can prove realizes some ideal functionality, we can then go ahead and compose that protocol with any subsequent protocol that uses that key to perform the desired cryptographic operation. I don't know how many of you are familiar with cryptography or have taken a cryptography class, but for those of you who have, you may be aware that there are, in general, two different ways of defining security. One of which is a so-called game-based approach, where you list out a bunch of security properties, and then you prove that your construction realizes those security properties. And the other is a so-called simulation-based approach, which is based on this ideal functionality that I was just talking about. And I think one advantage in general of this approach, of working via simulation-based security and by defining an appropriate ideal functionality, is not only the modularity that you get from this approach, but I think it's also cleaner and it's much more clear, at least in some cases, it can be much more clear by looking at the ideal functionality exactly what security guarantees you achieve. And sometimes with a game-based functionality or game-based definition, I should say, it becomes rather complicated because you may have multiple different definitions. It may be unclear how they interact with each other, and it just becomes a little bit again, depending on the context and depending on what exactly you're doing, it may be more complicated to understand exactly what security guarantees are being achieved. And I think that's the case in particular with DKG, that working via an ideal functionality gives you a cleaner approach. We're interested in this talk in the round complexity of fully secure DKG. We're going to be looking at the so-called honest majority setting. In fact, honest majority is required in order to achieve full security in this setting. Honest majority means that if we have a collection of n parties who are going to be sharing this key, then we need strictly fewer than n over 2 of those parties to be corrupted. And we'll actually achieve the maximum subject to that bound. We'll be able to achieve security as long as strictly fewer than half are corrupted. And as far as the communication model goes, we're going to, for the purposes of this talk, assume that the parties are interacting over a synchronous network. So the protocol is going to run in a series of rounds. And we're going to also assume that the parties have access to a broadcast channel. We're going to also allow, for those who are familiar with the concept, we're going to allow a rushing adversary, which means that in each round of the protocol, the attacker who's compromised some set of the parties is going to be able to wait until the honest parties send all their messages in that round. And then based on what the honest parties send, is going to be able to then respond and send its own messages for that same round. Yeah, and also I should say, I should have said this at the beginning, but if there are any questions, you can feel free to stop me at any time. It's a pretty small room. It's a pretty informal talk, so you can feel free to ask questions at any time. Great, and what we're going to show is several results about the round complexity. I'm going to mention, without giving the full proof, but I'll talk about a lower bound in this setting, showing that we cannot have one-round protocols for fully secure DKG. And one of the things that I think is interesting about this result is that it holds regardless of any setup the parties may have. And I'll talk in a moment about exactly what I mean by setup. But regardless of what setup the parties have, there are no one-round protocols. And we'll also then show, on the flip side, we'll look at different upper bounds, different feasibility results for fully secure DKG in this setting, and show several different round optimal protocols with trade-offs in terms of their efficiency, their required setup assumptions, and also cryptographic assumptions that we need in order to prove them secure. So just to give you a sense of what I mean by DKG in the discrete logarithm setting, let me define a little bit of notation. So I'll use n throughout this talk for the number of parties. I'll let t be an upper bound on the number of corrupted parties. So again, t plus 1 is the threshold required to perform the cryptographic operation, but t is going to be a bound on the number of corruptions that we allow. I'll use this fracture G, I guess, for a cyclic group of prime order Q. And I'll assume that we have fixed in advance some generator, little g, of that group. And I wanted to introduce the notion of Shamir secret sharing for those who haven't seen it before. It's a classic technique. It goes back to the late 1970s. And it's really amazing how useful this technique can be. The idea basically is that if you want to share a secret value, in this case, a secret value S in the field of elements mod Q, what you do is you basically pick a random polynomial that is equal, whose constant term is equal to the secret you're trying to share. So what does that mean? Well, it means basically you're going to pick random coefficients for or you're going to pick random coefficients for each coefficient of the polynomial except for the constant term, which is going to be set equal to S. You set the degree of your polynomial equal to the number of corruptions you want to be able to tolerate. So in this case, if we want to tolerate t corruptions, meaning that an adversary who learns up to t of the shares that we're going to define in a minute should still not learn any information about the secret S, and that's how we're going to set the degree of this polynomial. And then we are going to pick, well, just notice that setting the constant term equal to S is equivalent to requiring that evaluating the polynomial at 0 is equal to the secret you're interested in sharing. And then we're going to set the so-called ith share, in this case, that I'll call sigma I. We're going to define that to be equal to the evaluation of this polynomial at point I. Okay? So if we have n parties altogether, we're going to define these n shares, right, sigma 1 through sigma n, defined by evaluating the polynomial, this random polynomial that we chose, at the n points 1 through n. And in this case, if we assume a trusted dealer, then what we would have is we would have that dealer who knows S pick the random polynomial, define the shares, and give the ith share as sigma I to the ith party. And it's not too hard to show. It's a nice exercise, I think, that any t shares don't reveal anything about S. So if you have any t shares, regardless of which t parties might be corrupted, and regardless of which t shares an adversary might therefore learn, those t shares actually leak no information about the secret value S. And basically the way you would do that is you can set up a system of equations, and you can see that the system of equations is essentially underdefined, and the free term of this polynomial S, it can be anything, and therefore the parties learn no information about the secret. I was thinking earlier, actually, when I said it could be a nice exercise, I think it's a nice exercise for European students. I think in America, I would not give it as an exercise, but you guys are very smart. So, and you can also see that you can recover the secret from any t+1 shares, right? And that's just by polynomial interpolation. If you have t+1 evaluation points of a polynomial of degree t, that uniquely defines the polynomial, in particular that defines the constant term, and so we can reconstruct S. Now, this, of course, doesn't give you a full threshold cryptosystem. You have to do a bit of work to then use these shares in an appropriate manner. Also, the way I'm describing it here is assuming a trusted dealer, and we want to get rid of the trusted dealer. But this is just setting up basically a tool that we're going to use in our protocol. One thing I also want to point out is that you can do things a little bit differently as well. So if we fix some set C, which is going to correspond to a set of parties that are corrupted, and since we're bounding the number of corruptions by t, that set is going to have size at most t. We can also describe the sharing of S in a slightly different way, or we can do the sharing of S in a slightly different way, and it's still actually secure. What we can do is we can allow the adversary who's corrupted the set of parties of size at most t, we can even allow the adversary to choose the shares sigma I that it wants those parties to receive. Right? You can imagine that the adversary is basically telling the dealer, okay, I want my share to be this particular value sigma I. And what the dealer then does is chooses a random degree t polynomial subject to the constant term being equal to S, but also subject to the additional set of constraints that f of I is equal to sigma I for I in the corrupted set. Okay? And what you can see is that what I had on the previous slide corresponded to the case where the corrupted set was empty. And in that case, basically, it's equivalent, choosing the high order t coefficients of the polynomial is equivalent actually to setting the values of the points on any evaluation set to be random values. So in this case, once you've chosen the random polynomial subject to this set of constraints, we then set the ith share equal to f of I like before for all the I outside the corrupted set. Okay? And what you can see in particular, actually, is that if the attacker corrupts the maximum size set of parties, if the attacker corrupts exactly t parties, then for a given secret S, actually, there's no freedom left in the second bullet, right? So if you pick a degree t polynomial subject to, in this case, t+1 constraints, we have the t given by the adversary, and then the additional constraint on the constant term, that uniquely defines the polynomial. Of course, the attacker doesn't actually know S, so S remains hidden. The point of all this is to say that allowing the adversary to pick the shares that it wants to receive doesn't actually compromise security of the secret sharing. The secret S remains hidden, and of course, any t+1 parties are still able to reconstruct and obtain the secret. Questions about that? I think this is probably less standard, but it's not hard to see also that it holds as well. Good. Yeah, and in fact, right, you can claim something a little bit stronger. So even if the attacker later corrupts more parties up to the bound t, they still reveal nothing about the secret S. And the goal of a distributed key generation protocol is going to be for these n parties to run an interactive protocol that allows them to generate a common public key that I'll denote by y. And as typical in the discrete logarithm setting, we're going to want that value y to be equal to g to the x for a uniform exponent x. And along with that public key y, we also want the parties to end up, after running the protocol, holding a t+1 out of n secret sharing of the discrete logarithm x of that public value y. And in addition, I'm going to impose another requirement on the protocol, which is that at the end of the protocol, all the parties will know these, what are sometimes called commitments to all the other parties' shares. So I'll use, well, I guess I didn't define the notation here. I think I use yi to represent g to the sigma I, where sigma I is the share of the ith party. And this is actually very useful in a lot of threshold protocols. It's not strictly speaking required, but in many protocols for threshold signing, et cetera, it's very common to have these values available. And the reason they're useful is because they allow parties to then prove correctness of things that they do with their secret value sigma I. So we'll just allow that to happen here, and we'll actually require that because some protocols need it. And the only thing I'll just mention here as a little footnote is that throughout the talk, I'm going to assume that we're doing Shamir secret sharing. The only other really I mean, you can consider other secret sharing schemes, but the only other really common case is when you have a threshold set equal to n, and in that case, you might want to do n out of n additive sharing. You could also do Shamir sharing in that setting, but sometimes additive sharing is a little bit simpler to work with. And you can basically, like the ideal functionality I'm going to give, you can generalize for other secret sharing schemes, and I'm just assuming Shamir for concreteness. So let me come back to this question I mentioned a few slides ago about the setup that the parties may have. And I think this is something that, well, to some extent, it's a lot of people leave it implicit when they talk about protocols, but here I actually want to make it explicit, in particular for the lower bound we're going to show, but also for the protocols we're going to show. We're going to look at different setup assumptions that we might have when running the protocol. What are some common examples of setup that we might assume the parties have before running the protocol? Well, one common example is the assumption of a common reference string, or a CRS. So this would basically correspond to a trusted random string that all parties have access to, that they can use throughout the protocol, and it's outside the ability of the attacker to tamper with that string or to bias that string in any way. Another example that comes up often is the assumption of a PKI, or a public key infrastructure. This would basically mean that each party would have a local public and private key pair that they might use for encryption, say, and that all the other parties not only know each other's public keys, but they also agree on the public keys of every party. So this is what I would mean by a PKI. But even things like a random oracle model can be viewed as a form of setup. If you think about a random oracle as basically a completely, well, you can think of a random oracle as just a very large common reference string in some sense that the attackers have random access to. And in that sense, it's some kind of a shared state that the parties have access to before running the distributed key generation protocol. And then one other example, which is, I guess, maybe less common in general, but actually very common in the context of secure multi-party computation, is so-called correlated randomness. So here, basically, we imagine that the parties have each have some secret state, but those secrets are correlated in some particular way that they can then exploit in the context of running the protocol. And we'll see some examples of that later on in the talk. Yeah, one thing I'll just mention is that ideally, you would want some whatever setup the parties have, whatever common state they have, should suffice for an unbounded polynomial number of executions. It's sort of less interesting. I mean, you could assume that the correlated state is, you know, a t+1 out of n sharing of a secret, and that's okay. That actually would solve the problem, quote unquote, but it only gives you one key. It doesn't allow you to then generate a second key. So we're interested more in setups that allow you to generate an unbounded polynomial number of keys. And what are some of the desired security properties we want in this setting? So in general, of course, we want the protocol to be correct. We want it to achieve the functionality that we talked about earlier. So the honest parties should indeed hold a correct sharing of X. We can't really say anything about the outputs of the malicious parties. The malicious parties can basically output, you know, whatever they like at the end of the protocol. But in our context, where we're going to assume an honest majority, we're at least going to want the t+1 honest parties, or I should say the at least t+1 honest parties, because the attacker may corrupt fewer players. We want them to have a correct sharing of the discrete logarithm X of the public value Y. And we also want them to end up with correct commitments to each other's shares. We also want secrecy to hold, right? We want exactly the property that when the attacker corrupts up to t parties, the attacker should learn nothing about the secret value X. And these are kind of standard properties that will always be required for any DKG protocol. But we're going to be interested also in additional properties. And this is kind of what I mean when I say fully secure. First of all, we're going to require that the key that's output by the protocol, the public value y, should not be biasable by the attacker. So we want the public value y to be completely uniformly distributed. And we don't want the attacker to have the ability to bias that value at all. And this is actually one of the, well, I mean, it goes along with the next property, but this is one of the major challenges in designing a fully secure protocol. And along with that, we're also going to require robustness, sometimes called guaranteed output delivery. And this means that no matter what the attacker does, the honest parties should end up with a valid sharing of the public value y that they generate. Okay, we don't want the attacker to have the ability to abort the protocol by whatever it does, whether the attacker aborts or whether it does something malicious or et cetera. We don't want them to have the ability to prevent the protocol from generating output. And there may be other properties you want as well. And as I said earlier, the way we're going to kind of define or impose all these requirements at once is by defining security via an appropriate ideal functionality for what exactly we're trying to do, and then realizing a protocol for that functionality in a simulation-based framework. So there are multiple different ideal functionalities that you can consider for distributed key generation. Even if you want full security, there are different, well, yeah, there are all kinds of different variants you can consider. You can look at the paper for some examples and discussion. I'm going to just focus on one particular ideal functionality in this talk. And so this basically is actually a simplified version of the functionality, slightly simplified. The only real simplification here is that I'm assuming that the attacker corrupts exactly T parties. Actually, one thing to be aware of in general in this context is that a protocol which is secure for corruption of T parties, this is a general statement, you can have examples of protocols secure for T corrupted parties that are not secure for T-1 corrupted parties. That's a good exercise also to think about how that can be. But anyway, here for simplicity, I'm going to assume T corruptions. And the way the functionality is going to work is that we're going to first allow the attacker to choose its own the shares for the corrupted parties. This corresponds to what I said earlier in the context of Shamir secret sharing. So we're going to allow the attacker to specify the shares sigma I for all the corrupted parties. Then the ideal functionality is going to choose a uniform value x and set the public value y equal to g to the x. We're going to then define the polynomial, or we're going to choose a polynomial f of degree at most t, subject to the constraints that f of 0 equals x and f of I equals sigma I for, oh, that's a little typo, but anyway, for I in the corrupted set. And we're going to then use that polynomial to define the shares sigma I for all the remaining parties. And then we're going to also we're going to define these public commitments, yi equal to g to the sigma I for every party. I'm going to let capital Y just denote the vector of these commitments. And then for each party, from 1 to n, we're going to send them the public value y, their share sigma I, and then this vector of commitments to all the other party shares, capital Y. Okay. And one thing to note in this ideal functionality, well, let's actually think about what properties it guarantees. So the first thing I want to highlight actually is that there's no possibility of abort here. So if you're familiar with ideal functionalities in the context of secure computation, you may, I mean, especially in the two-party case, for example, you may be familiar with the fact that some functionalities give the attacker the explicit ability to abort, whether that's before they get their output or after they get their output. This functionality does not allow that. So regardless of what the attacker does, all honest parties are going to indeed get the output from the functionality. The functionality clearly guarantees correctness, right? It assures that the vector of commitments y corresponds to the shares that each party holds. And it also guarantees secrecy because the private exponent x is chosen uniformly at random. As we said earlier, even if we allow the attacker to specify T shares of the secret sharing of that value, that still doesn't give the attacker any information about the value y. Actually, I should just clarify that a little bit, right? So the secret x is secret up to the fact that, of course, information theoretically is revealed by the public value y. But of course, we have to reveal y. That's part of the definition of the scheme. And what we want to say is that the DKG protocol leaks nothing about the secret exponent other than what the attacker can derive from the public value y. Question? Oh yeah, yeah. So I think so. Right. So this functionality also guarantees no bias. So why is that? Because the exponent x is chosen uniformly at random, and then the public value y is set equal to g to the x, and that's the value that's returned to the parties. So there's no possibility in this functionality for the attacker to have any bias on the value y. Yeah, that's a good question. I think so. First of all, I mean, in general, you don't want bias because if the attacker can introduce bias, I mean, they might be able to, for example, if you allow arbitrary bias, the attacker could force X to be in some interval, and then it would make the discrete logarithm problem easier. There are what's the way to say it? There are particular kind of biases that you can show don't affect security of the value y that's returned. And maybe that's what you're getting at. So for example, if you, yeah, I guess if you require, and maybe it depends a little bit how you define it, but yeah, if you require that sort of the view of the adversary, that even given the view of the adversary, X remains uniform, then that would rule out that example. I think the other reason for not wanting bias is because sometimes there are protocols that actually do things based on the public key, and if the public key, if you can force the public key, so let me actually give an example of bias that's acceptable for some purposes. If we allowed the attacker, for example, to observe y and then give a random shift delta, and then the actual output public key would be y times g to the delta, there are cases where you can prove security of the subsequent protocol even in that case, although you have to work at it and it's not clear how to prove it for other cases, which is also why you want to avoid bias. But if you're using the public key y, also to derive some coin that you might do something with, then you would want y to be unbiased in general. Yeah, actually, in the paper, I mean, we define also this version of a biasable DKG, where exactly the attacker can introduce this shift. But yeah, but then it's sort of not immediate how to compose that with arbitrary other protocols afterward. Other questions? Yeah, and one thing I should point out at this point is that this is impossible to realize unless you have an honest majority. And this follows from basically results on unbiasable coin tossing from Cleve, who showed that, because this implies coin tossing essentially, right? I mean, yeah, and let's just say it implies coin tossing. And we know that unbiasable coin tossing with guaranteed output delivery is impossible to achieve without an honest majority. So in the prior work, there has been actually a lot of work, especially recently, on distributed key generation protocols. Very few of these actually consider the case of full security. The most round efficient prior work that gives an explicit fully secure DKG protocol is a 6-round protocol from 2007. You can also use generic results from secure computation to get low round protocols. You can get a 3-round protocol, or I guess prior work implies a 3-round protocol with a CRS or a 2-round protocol with a CRS and a PKI. The one thing I would say about those protocols is that they're very complex and based on very strong cryptographic assumptions. I think the 2-round protocol minimally requires FHE, and I forget exactly which one is which, but one of them requires IO as well, obfuscation. So it's interesting to still see what we can do based on more standard assumptions. On the flip side, the known lower bounds for the round complexity of secure computation with guaranteed output delivery don't apply here and don't give us any lower bound. And it's actually interesting to think why, and I think it's an interesting open problem for people who like to look at this stuff. The lower bounds on round complexity of MPC, they give lower bounds for particular functions. And specifically, the functions that they give lower bounds for are functions that have a requirement both of input privacy and guaranteed output delivery. And in the context of DKG, it's essentially a no input functionality, right? The honest parties have no input. We're not trying to, we're trying to preserve privacy of this value X, but there's no input of the honest parties that we're trying to ensure privacy for. And if you look at the proofs, the known lower bounds in the context of MPC, it's not clear how to adapt them to the case of a no input functionality. And I think it's kind of a nice open question, actually, maybe to characterize which functions require some minimal number of rounds in that setting, and maybe you can show a hierarchy of what's possible. Okay, so let me just quickly go over the impossibility result. We show that fully secure DKG is impossible in one round, regardless of prior setup. Actually, it's interesting because this result holds even if we don't require robustness, and even if we want to tolerate only a single corrupted party. So it's kind of a strong impossibility result in that sense. It's really only relying on the unbiasability property. And I'm just going to sketch the idea. I'm not going to go into the detailed proof. But let me first define a property of a DKG protocol. I'll say that a DKG protocol is statistically unbiased if an honest execution of the protocol yields a close to uniform key. Okay, you would expect this for any DKG protocol. And the theorem is that there's no one-round statistically unbiased DKG protocol that one securely realizes this DKG functionality I had on the earlier slide, regardless of any setup the parties have. And let me just give the flavor of the proof. So the idea is that we'll show, and it's just going to really be a recap on the next slide. I'm not going to go through the equations. But the idea is to show that some party in the protocol must have the ability to bias the key by exploiting the fact that we allow a rushing adversary. That means that, again, the fact that we allow the adversary to see the messages sent by honest parties before sending their own messages. So how are we going to use that in the proof? So just imagine for simplicity that we're even trying to generate just a 1-bit key. And we want that 1-bit key to be statistically unbiased between 0 and 1. And we can consider the following generic attack by party PI trying to bias that key toward a particular bit B. What that party is going to do is simply, so imagine we have a one-round protocol. We're going to show a contradiction. What this attacker is going to do is receive messages from all the other parties, compute the key that would be output if it runs the protocol honestly using using true randomness RI. And if the output of the protocol, right, it can do that because we assume a one-round protocol. At the end of the protocol, everyone has the ability to compute the output. If the output is B, it's happy with that output, so it just runs the protocol honestly with the honest randomness RI. And if the output is not equal to B, it just chooses or it samples fresh randomness RI prime and runs the protocol using RI prime. So it's really a very simple strategy for implementing an attack. And what you can show is that there must be some party I and some bit B such that this strategy noticeably biases the output of the protocol toward B. And if we have a if we have a protocol which is fully secure, then this should not be possible. Okay? So this shows that one-round protocols are not possible with a statistically unbiased key. I'm assuming broadcast here, yeah. Well, if there's no broadcast, then it's even. I mean, you can't do one-round protocols even with broadcast, so you can't even hope to do it without broadcast in that sense. But then it wouldn't be a one-round protocol, right? Then it would be like an n-round protocol. Well, it depends maybe how you define it, but I mean.
People will change, right? Because somebody needs to be the last party.
Yeah, I mean, the problem is, the main issue is like, how do you decide the random order, right? So what are they basing the random order on? I'd have to think about it a little bit, but I think the main point is that this would not be a one-round protocol anymore. At the minimum, it would have to be 2 rounds. Right, like if you have half the parties go in 1 round and then half the parties go in the 2nd round, this would be a 2-round protocol. Good. Okay, so what about 2-round protocols? So let me actually try to get at the difficulty in this setting and kind of why I found this to be a fun problem to work on. So just thinking about how we might construct a protocol that runs in 2 rounds. So the natural way to go about this is as follows. So what we're going to do is we're going to have 1 round where parties are going to basically commit to their shares, and then a 2nd round where parties decommit their shares and then use the decommitments to reconstruct the output of the protocol. And then in the simulation, what we're going to do is we're going to set up a simulator who can extract the corrupted parties' inputs from the 1st round, or I should say their shares rather than their inputs in the 1st round, and then they can equivocate on the honest party shares in the 2nd round, and then they can basically force the output, the key that's output by the protocol, to some desired value. Right? This is a natural way, if you've worked in secure computation, to go about constructing a 2-round protocol. And the problem with this is that the corrupted parties, or some set of the corrupted parties, can abort in the second round. Okay, so this works fine if we assume that the adversary never aborts. Well, I mean, well, it's not even possible really, because it's not only the abort that's a problem, it's also the they can send garbage in the second round. So it's not just about aborting, it's about not following the protocol completely. So sure, if you assume that the attacker follows the protocol, honestly, or maybe picks its randomness in some biased way and then runs the protocol honestly, this can work. But it's going to fail completely if some of the malicious parties can abort in the second round, right? So just think about why that's the case. So in the first round, the simulator was able to extract the effective shares of the corrupted parties. And then the simulator has to open in the second round some decommitment corresponding to the honest party's shares. And it can do that maybe however it likes, depending on how we set up the simulation. But then based on that, an arbitrary subset of the corrupted parties can choose to abort. And based on which corrupted parties abort and which ones don't, that will affect the output of the protocol. But that's exactly what we want to prevent. Question?
I do have one question about the abortions. Since we assume that the party that aborts is an adversary, can we just publicly simulate what this adversary would be doing with like non-validated?
So it depends how you implement it. Depends how you implement it, right? So if you had a way to not the answer is no. So think about it. So first of all, if you're just going to take that party and say, okay, party one aborted, and we know they're malicious, now everybody's going to rerun the protocol with party one kicked out or simulating what party one would do. So first of all, that's going to introduce bias, right? Because again, you have the same attack where party one can see whether it likes the output of the output value y, and if it likes it, it'll behave honestly. If it doesn't like it, it'll abort and force a rerun of the protocol. Second of all, even if you had some way to continue the execution of party one using the value that it committed to in the first round, which is kind of what you do in MPC when you run protocols based on parties' values, that's already going to add one extra round. And we want to avoid the third round. We want to finish everything in 2 rounds. So yeah, it's not so easy. Yeah. But we'll effectively do a similar kind of thing, but compressing it all into 2 rounds. Right. So intuitively, what we need is our protocols with the following properties: that the key is determined at the end of the first round based on the parties' effectively commitments to the shares that they want to use in the protocol. But that should hold regardless of which corrupted parties might abort in the second round. And of course, it has to be the case that the adversary itself cannot determine what that key is at the end of the first round, or else you have that same rushing strategy as I showed before that would allow the attacker to bias the key, this time doing that in the first round rather than in the second round. And so we show various positive results for 2-round protocols for fully secure DKG. And like I said earlier, they vary on the efficiency, which I don't have in this table, but also on the setup they require and the assumptions that they need. The first protocol we have is based on a common reference string and a PKI, and requires non-interactive zero knowledge and public key encryption. We then show how to remove the PKI and get a protocol based only on the CRS. But this requires stronger assumptions, actually. It requires not only non-interactive zero knowledge, but also multi-party non-interactive key exchange. And then we show a protocol in the random oracle model based on correlated randomness that can be set up between the parties using a 1-round pre-processing phase. So this is basically going to be a 1-round pre-processing that the parties run, after which they can then run an unbounded number of DKGs in only 2 rounds per DKG. And this actually requires no assumptions beyond the random oracle. And then surprisingly, we also show a 1-round protocol. And this is based on a CRS and 2 rounds of pre-processing. And I hope someone has a question of how we can have a 1-round protocol when I proved that 1-round protocols were impossible a couple of slides ago. And the reason is because actually what we showed earlier is that fully secure DKG is impossible for statistically unbiased protocols. And although it's natural to assume that any protocol realizing that ideal functionality I showed would be statistically unbiased, in fact, that's not necessary. And in fact, you can have protocols that are only computationally unbiased that also realize the functionality. And for computationally unbiased protocols, you can actually get a 1-round protocol. And this is based on non-interactive zero knowledge and one-way functions. So I'm not going to have time to cover all of these, I hope I have time to cover maybe two of them, and I'll leave you with a teaser for the other ones. So let's actually go through the first protocol, which is based on a CRS and a PKI. It's kind of just a nice warm-up protocol, and it's kind of indicates kind of how a general approach for how we can solve the problem. And then I think we'll also have time to cover the second protocol as well, which I think is I really like it, even though it's not practical because of its reliance on multi-party NIC. Okay, so let's look at the first protocol. The starting point here is, and this is common to a lot of DKG protocols, the way they work, regardless of what the round complexity is. The starting point is going to be that each party PI is going to choose their own contribution to the value, to the secret value X. So each party PI is going to choose a uniform value Xi, and then use Shamir secret sharing to share Xi with the other parties. The parties can then sum their shares locally to obtain shares of the secret value X, which is defined as the sum of the contributions Xi from each party. And the problem, of course, I mean, one set of problems is that the corrupted parties can send inconsistent shares, right? If I'm a corrupted party P1, I can send shares to all the other parties that don't form a valid T+1 out of n secret sharing of any value. And just by doing that, I can ruin correctness of the protocol. Right now, not every party will end up with a correct secret sharing of the value X. And there are sort of standard techniques for dealing with this, right? It falls under the line of work on verifiable secret sharing, but the standard techniques for dealing with it all require at least 3 rounds. What we're going to do instead is we're going to assume a common reference string, and then we're going to use non-interactive zero-knowledge proofs in order to force correct behavior of the adversary. Now, one thing you can see here right away is that NSAK proofs are going to be useless for proving correctness of what a party does if it's sending values by private channels, right? If I'm sending a value, a share of my value Xi to party 1, and then sending another share to party 2, but they can't see the shares that I'm sending because they're being sent over private channels, then I have no way of proving consistency of those values because there's nothing really, there's no NP statement effectively that I can reason about. So what we're going to do instead here is, this is where the requirement of a PKI comes in. What we're going to do is we're going to simply instantiate the private channels, as it were, by using public key encryption. So I'm going to use public key encryption to encrypt each share under the public key of the corresponding party. And now I can define a well-formed NP statement about consistency of the values that I've encrypted, and I can now apply non-interactive zero-knowledge proofs. Now, this alone is not going to be enough to prevent bias, because even if the parties, even if we have the parties commit to Xi before sharing it, the corrupted parties can still introduce bias by aborting, right, by failing to basically open their value Xi. So what we can do is we can overcome aborts if we set things up such that all parties learn shares of Xi in round 1. And if you do that, then at least the T+1 honest parties are not going to abort in round 2. And this kind of comes back to the idea suggested earlier, that if we can set things up in such a way that parties are able to continue the protocol, even if a party aborts, then it doesn't matter whether they abort or not. And of course, like I said, we want to do this without introducing a third round. So we want parties to open up to all the values that they need to in round 2. And then it doesn't matter which parties abort in that round, because every contribution will be taken care of in the values that honest parties reveal. Yeah. And for simulation, we're going to need the ability for honest parties to equivocate in round 2, and you can do this using a second round of NISIX, essentially. So what's the overall protocol going to look like? So in round 1, we'll have each party PI choose a uniform value Xi, like I said, and it's going to broadcast encrypted shares to all the other parties, and then give a non-interactive zero-knowledge proof of correct behavior of that all those encrypted values form a valid T+1 out of n secret sharing. And we can let good denote the set of parties who give correct proofs, right? Those are parties who basically shared some value correctly. So notice, by the way, right at this point, it could be the case that some malicious parties abort, or maybe they send things with incorrect proofs, but that won't allow them to bias anything, even if they're rushing, because at this point, parties don't know the values of all the shares. They only have the shares that they've received, and the malicious parties haven't received yet enough information to know what the final value y is going to be. And then in round 2, each party PI, right, notice that all parties agree on the set of good parties. They recover their shares by decrypting. They add them up to get their share sigma I. And then they broadcast the value g to the sigma I, which is the commitment to their share, along with a non-interactive zero-knowledge proof of correct behavior. So what does it mean to give a non-interactive zero-knowledge proof? It means a proof that of all the ciphertexts I received, I decrypted them all correctly, I summed them up, and I got a value sigma I, and now I am indeed broadcasting this value g to the sigma I. And we can again have malicious parties who abort here, or maybe send incorrect values, but any values yi that are broadcast by an adversary with incorrect proofs, right, proofs that fail to verify, are simply going to be ignored in the next step. And then what we do is we're going to interpolate all the non-ignored yi in the exponent to obtain the public key y. I didn't write it here, but you can also do the same interpolation in the exponent to get the yi for all parties, even those who have aborted. And this will define a value y equals g to the x, where x is implicitly being set equal to the sum over the good parties of their contributions xi. Oops. So the key insight, I guess, is that for any I in the good set, the honest parties have enough information to recover their contribution in round 2. So again, in round 2, or let me say it differently, after round 1, we've defined a good set of parties. And the claim is that at that point in time, this value x, which is the sum over the good parties of the xi, that value is defined. And regardless of what aborting behavior the attacker has in round 2, that's the corresponding value that the parties are going to output. Sorry, what did I say? I said regardless of any aborting in round 2, all the honest parties are going to recover y equals g to the x for x equals that value in round 2. So even if all the malicious parties abort, it doesn't matter. All the honest parties already have enough information to reconstruct that value xi. So the value of the key is defined after round 1, no matter what the attacker does in round 2. But yet the attacker, of course, doesn't know the key at the end of round 1. Yeah.
The concrete instantiations of the encryption and the NISIC, or you just
Yeah. So you can actually instantiate this you can do these non-interactive zero-knowledge proofs by putting also a Payet public key in the CRS, and then encrypting using Payet, and then giving proofs of equivalence, like we were talking about yesterday, between the values that you encrypted and these Payet values. And interestingly, there was prior work using that in another setting, in the dishonest majority setting for DKG, and you can give relatively efficient proofs in that case. I mean, it's not like super efficient, but it's like concrete, and you can implement it. Good. So just majority, yeah, is enough. Okay. So let me give one more protocol, and I think we can kind of finish there, and maybe I'll take questions if there are any. So here we want to give a protocol in the CRS model only. And I think the challenging thing here is that the PKI seems really essential in the first protocol, exactly because we wanted to have the attacker be able to prove things about the values it shared. And it seems, very difficult to do this without any kind of a PKI. So it's a natural question to see whether it is indeed possible to avoid it. And for simplicity, what I want to do is focus just on coin tossing in the 3-party setting. You can go from coin tossing. I mean, I think it illustrates the main ideas. You can go from coin tossing to DKG with a little bit of work. It's not maybe super difficult. And you can extend it to the n-party setting using T+1 party non-interactive key exchange. So what is T+1 party non-interactive key exchange? Well, basically, 2-party non-interactive key exchange is just Diffie-Hellman. It means that each party broadcasts a value, and then, or there's no broadcast in that case, each party sends a value, and then based on that, they can recover a shared key that an eavesdropper doesn't know. T+1 party NIKE would be the generalization of that to T+1 parties. Okay, we do have actually 3-party NIKE based on pairings. 4-party NIKE and above needs more exotic assumptions in order to construct. And as before, the intuition here is that after round 1, we want now the coin, there's no public key per se, but we want the coin to be determined regardless of what the corrupted party does. So if we're in the three-party setting, then we only have one corrupted party. So regardless of what the corrupted party does in round 2, the coin should be determined at the end of round 1, but the corrupted party, of course, should not be able to compute it after round 1. So the core idea is that in round 1, we're going to use a two-party non-interactive key exchange, so think just Diffie-Hellman key exchange, that's going to allow us to define a coin for each pair of parties. And then in round 2, each party is going to reveal the coin for all pairs that it's a member of. And in order to prevent cheating, we're going to use a non-interactive zero-knowledge proof to prove that the value we opened is indeed the correct value of the coin. So let's see why this works. I don't know if I have I guess I didn't have an animation here. Let me just see. Okay. Yeah, so why is this going to work? So think now concretely about the case of three parties, and I guess you don't have a marker here. Doesn't matter. So let me describe it in words and we'll see. So we have three parties, right? And we have parties 1, 2, and 3. We'll have each pair of parties run Diffie-Hellman key exchange in the first round. So what does that mean? They're each going to broadcast, g to the x1, g to the x2, g to the x3. In this case, that defines 3 shared keys, right? One between parties 1 and 2, one between 1 and 3, and one between 2 and 3. Okay. Now imagine party 3 is corrupted. So party 3 knows the coin, the value shared by the Diffie-Hellman key exchange between itself and party 1 and between itself and party 2. Right? It knows, let's call them K1, K13 and K23. But it doesn't know anything about the shared key between parties 1 and 2, K12. So there's still some randomness. And if we define the key to be, if we define the coin that's output to be the product of all those values, right, that value will still be uniform. Now in the second round, what we're going to do is we're going to have each party broadcast all the keys, all the shared keys of the pairs that it's a member of. Right, so party 1 is going to broadcast the shared key K12 as well as the shared key K13. Party 2 will broadcast K21 and K23, and party 3 is supposed to broadcast K13 and K23. But of course, the attacker can choose to abort, and maybe even abort depending on what the value of the key K12 ends up being equal to. The point is, it doesn't matter, because even if the attacker aborts and doesn't broadcast K13 and K23, those values are going to be broadcast by the other honest parties in that pair. Okay? So regardless of what and of course it can't cheat on the value of broadcast because we're going to tie its hands using the non-interactive zero-knowledge proofs. So what this means then is that regardless of what the attacker does in the second round, the key, which is the product of all these pairwise shared keys, is going to be well defined at the end of round 1. Okay? And you can go ahead then and generalize that to the case of any number of parties. So this is basically what I said here. For every pair, the properties we're using are that for every pair of parties, at least one is honest because we're in this three-party, one corruption setting. And there's also one pair of parties that's entirely honest. And if you imagine setting up a combinatorial set system where that holds for any t+1 parties, you can generalize this idea if you have t+1 Nike to get a 2-round protocol in that setting as well. So I'll just briefly, I'm not going to go through the protocol. What I will say is that this third protocol, based only on the random oracle model and 1 round of preprocessing, I also really like. It's a nice protocol, but the nice thing about it also is that it's really efficient, right? Because it's not using any non-interactive zero-knowledge proofs. It's only using hash functions that are modeled as random oracles. I mean, of course, we also have the exponentiations that are required for the DKG. But otherwise, it's it can be a really efficient protocol, especially for moderate values of T and N. So, if you're interested, I would encourage you to look at that. You can implement it. It runs very quickly. And I think it can actually be a practical protocol for, 5 parties up to 2 corruptions. And of course, the last protocol, which I won't go into at all either, is showing how you can circumvent the impossibility result if you relax the notion of statistical non-bias to allow for computationally unbiased key, which is not statistically unbiased. And I'll leave that for the paper as well. So let me jump through this. There's not going to be time for this. Let me just leave with a couple of open questions, perhaps. I think actually there are still many open questions here, and it's a really nice. I think they're very fun problems, and I would encourage people to work on them. In addition to this open question I mentioned earlier, about lower bounds for general secure multi-party computation with guaranteed output delivery. These are more specific for the case of DKG. I think, first of all, I didn't actually mention this explicitly, but if you think about the non-interactive, the protocol that I showed based on non-interactive key exchange, if you generalize that to the case of general N and an honest majority, that protocol has complexity N choose T, basically because you end up looking at all subsets of the parties of size T. And so it's a very natural question to see whether that can be improved and whether you can get a protocol in the same setting, let's say with the same setup, that has polynomial complexity in N. Some of the protocols require pre-processing. So I didn't talk about those protocols, but the final two protocols both rely on some pre-processing that the parties run before any executions of the DKG itself. And it's natural to wonder whether that can be avoided and whether we can reduce the setup assumptions there. And then just in general, right, I think the real question is, can you do full two-round fully secure DKG in the plane model? And yeah, I guess you can interpret plane model any way you like, but really we'd like ideally to avoid all setup assumptions and just get a two-round fully secure DKG protocol. I really suspect that it's not possible, but if you can then prove impossibility, that would be great as well. I was not able to prove impossibility there. So I'll leave you with that. The paper's online, and I'll be happy to take any questions that you have. Sure. Yeah. I mean, I don't know what the best way to get them to you is, but I can. I guess it's on your computer. So, yeah. Thank you. Yeah.
And you going with the definition of unbiased, you mentioned close to uniform. What is close to?
Oh, so in that context, it was statistical closeness.
So this.
Yes, yeah. So I mean, what happens in the computational protocol is that actually conditioned on the setup, the key is actually uniquely determined. So nobody, the attacker can't compute it, but there's no entropy left in the key at all statistically. So that is an example. It's like pseudo-random. It's like a pseudo-random value of the setup. So that's an example of where you have complete bias. I mean, whatever you want to call it, there's no entropy at all. So it's not statistically close to uniform, conditioned on the setup, but it's still computationally uniform given the setup. But yeah, you can imagine other kinds of relaxations as well. Yeah.
Question about what's the difference of like the one round of processing between one round of the real proof?
Yeah, so the difference is basically, so maybe the question is, what's the difference between like one round of pre-processing and then a one-round protocol versus no pre-processing and two-round protocol? So the difference is that the pre-processing is done only once, after which you can run an unbounded number of DKGs. So like you run the pre-processing once, whatever many rounds it is, but then every time you want a new key, you just run a one-round protocol. No, it has to be some correlated randomness. Otherwise, you could do it during the protocol itself. So they're setting up correlated randomness. Yeah.
At some point, you use it pre-processing in the protocol. At some point, all the queries are kind of used up that will be pre-processing, and then the pre-processing has to be.
No, because it's basically yeah. So the way that it works is like I was saying earlier. The key ends up being a pseudo-random function of some value, and that value can be a counter. So you run out when you exhaust the counter, but this is 2 to the n. So you basically have an unbounded polynomial number of executions. Yeah. Yeah, so you're sending these n ciphertexts or n-1 to different parties, and then you're proving that, and everyone knows all their public keys. So you're proving that, you're proving that you encrypted a valid T+1 out of n secret sharing of some value. It doesn't have to be random. Yeah.
Because I don't know enough about how to set this up in practice, these broadcast channels. So I was just wondering how. So the public key assumption or PKI assumption, isn't it kind of something you still use in practice or have it somehow you don't need this if you want to execute this in practice.
That's a good question. So I can tell you that, one of the things that was very interesting was actually working for a company that was deploying threshold schemes, and you see like how things actually work in practice. And so in practice, right, what happens in that case is that they provision, some number of servers, and they're all communicating over a TLS channel, and they all therefore already have each other's public keys anyway. So you could imagine actually, right? You could get rid of that, and you could. So let me think actually. So I didn't. Let me think actually. So you'd have to think about whether the protocols would be secure, like against a man-in-the-middle attack, which I guess like we didn't really define what happens in that case here. Like if everyone's honest, but there's a man in the middle, clearly things are not going to work, right? But you have the TLS channels exactly for that reason, mainly for authenticity rather than for secrecy. You could get rid of those, and it's actually interesting. Like for example, if you're familiar with Frost, one of the interesting things about Frost is that it actually does not require secure channels. And most of the threshold protocols, I think, implicitly do, even though they're not always talked about explicitly. But my point was more that in practice, you anyway have them because you know the servers in advance and you're provisioning them. And so it's not really, actually, let me say it slightly differently. There are in general two settings for threshold crypto. One is where you're kind of managing the network and you have control, whether they're all, actually controlled by you or whether you're partnering with somebody, whatever, but you know in advance all the servers. And in that case, you would usually provision public keys and assume everyone knows each other's public keys. The other setting is like over the blockchain where people come and go, and then you might have hundreds of parties. And then perhaps PKI, I mean, I don't know, maybe you can use the blockchain to set up a PKI, but maybe you don't want to rely on it. But at least in the provision setting, it's PKI is anyway going to be there. Well, you don't want to necessarily do that, right? You might want to give guarantees that even if no one's corrupted, but you have a man in the middle. I mean, it's not clear actually what guarantee you would want. I mean, I guess like if the attacker can block everything, then clearly you can't have robustness. So you have to think about how you would define it in that setting. Yeah.
Good. Any further question? Not that. Let's thank John again for the report.